See if we can find this volume. So first thing, let's read it carefully to figure out the setup. We have the graph of a base of an object. We want to compute the exact volume of the object, given that cross sections perpendicular to the base, parallel to the y-axis, are equilateral triangles. Okay, perpendicular to the base, so they're coming straight out at us, and they are parallel to the y-axis. So then my slices are going to look like this. And notice that the distance across here is changing linearly at first. And I guess it's changing linearly next, but it's constant after that. So basically, we're going to have to break this into two integrals. So mine will go from 0 to 5 for the first integral, and then from 5 to the 7 for the second integral, because we're going to have two different formulas. So a cross section, this is going to be the base of a cross section, and it's going to come straight out at us, and it's going to be an equilateral triangle. So if that's the base of the equilateral triangle, then that's the base, and that's the base. Area of a triangle is 1/2 base times height. And if you use the Pythagorean theorem to solve for the height here, which will be in terms of the base, you're going to end up with the area for an equilateral triangle is the square root of 3 over 4 times whatever that base is squared. Again, you can calculate that if you want based on the Pythagorean theorem, or just look it up. So that's the cross-sectional area. I need to now figure out, okay, what is the length of that base? Well, that is a vertical length here, and it's changing, right? So at any particular time, that value is some y value. And down here, because of the symmetry, it's just the opposite of that y value right there. So the total distance across is just twice whatever y is. For the first part of this, there is a rise of 2 and a run of 5. So for the first part, y is just 2/5 x. So the first part of my integral, well, let's plug that in here. So we're going to replace the y with 2/5 x. So I have 2 times 2/5 x times there, which is going to be 4/5 x is my base. So then my area, the cross section, is the square root of 3, 4 times 4/5 x squared. So my first integral is x going from 0 to 5. Square root of 3 over 4. You might as well clean that up a little bit. That's going to give me a 4 squared over 5 squared times x squared, a bunch of constants hanging around, dx. So this is, again, my cross-sectional area, and I put that square in the wrong spot there. That's better. Get 4 squared, 5 squared, x squared up there. That cleans up a little bit. We'll get to that in a minute. I'm not done because I still have to integrate from 5 to 7, and there y is always 2 on my version. And so for the second part of this, my base is still twice whatever y is, and in the second part, y happens to be 2, so the base is always 4. Okay? Distance from here to here is always 4. Well, obviously. So plus, and again, that's my base, that goes in here. Square root of 3 over 4 times 4 squared dx. So again, the challenge on these problems is to come up with a formula for your cross-sectional area, and then use the given information to figure out how that cross-section varies. Sometimes it's with respect to x, sometimes it's going to be with respect to y. These ones happen to be x. The second one, x goes from 5 to 7. That's the hard part. Clean it up a little bit. So let's see, here we'll have the integral from 0 to 5, and this cleans up a bit. 4 goes into 4 squared, leaving a 4. So I can pull out the constants. So I'm going to get 4 square root of 3 over 25 integrating x squared dx. And then the other one is just a constant. So we can just leave that. And this only cleans up a little bit. 4 goes into 4 squared 4 times. For that one, we'll be integrating from 5 to 7 for square root of 3 dx. And so our antiderivative, let's box off some space here, is going to be 4 for the first one, square root of 3 over 25. Antiderivative for x squared is x cubed over 3. That one is going from 0 to 5, and then we'll add on to that 4 square root of 3 times x, the antiderivative for that constant, from 5 to 7. And at this point, it's calculator time. Let's see what we get. So for the first one, we have 4 square root of 3 over 25. And we are evaluating that for x equals 5 cubed over 3. And let's just make a note to ourselves that when we plug in 0 here, we're going to get a 0. So that's going to have, just going to make a note for reference, a minus 0, plus the next part, we're integrating this from 7 to 5. So we're going to have 4 square root of 3 times 7 and minus 4 square root of 3 times 5. Five to 0 on that one, 7 to 5 on that one. So I'm getting a total area of 25, let's call it 0.4034. This question said to find the exact answer. The exact answer is typed out right here. That can be cleaned up just a little bit, but not a lot. Oh yeah, I guess. Okay, let's take a moment to clean that up for fun. You've got, check, 4 square root of 3 over 25 times 5 cubed over 3 minus 0 plus 4 square roots of 3 times 7 minus 4 square roots of 3 times 5. And this is fun to clean up. 25, which is 5 squared, goes into 5 cubed 5 times. So that part's going to give me 4 square root of 3 times 5. I guess we can clean that up too. 4 times 5 is 20 square roots of 3 over 3. And then here, 4 square roots of 3 times 7 minus 4 square roots of 3 times 5. Well, 7 of them minus 5 of them is 2 of them. So that's going to give me 2 times 4 square roots of 3, which will be plus 8 square root of 3. And I suppose we can find a common denominator. So we'll divide and multiply by 3. 8 times 3 is 24 plus 20 or in the wrong order, 20 square roots of 3 plus 24 square roots of 3 all over 3 is going to give us 44 square roots of 3 over 3. Let's see if that matches my approximate answer. Again, hard part of these is not necessarily the antiderivative. It's not necessarily evaluating the antiderivative. It's coming up with a formula for the cross section. And that's always going to be in two parts. You have to figure out how your cross-sectional area changes given the conditions that you started with. That's the hard part. Everyone's a new adventure. Enjoy.